Oh shit.
No, all good. Hello, hello. Good afternoon. So basically the week eight's like a doozy, and I want to go over a couple notebooks in addition to the actual final activity. But yeah, there's a lot I want to talk about here in the next hour. So yeah, hello, welcome to week eight's the live session, whenever and wherever you're watching around the world. I'm still Alexander Booth, your instructor and facilitator for the course. And we got a lot to dive into this week. So hopefully you watched last week's live session in week seven. Not only did we kind of reintroduce machine learning and kind of what it means to operate within the machine learning lifecycle, but I also went a little bit above and beyond, introduced some more advanced metrics for classification, as well as pre-processing and production ML, which we went into in great depth in the week eight module and media set. So, as I said in my recap video, if you watched or kind of paid attention in some of the live sessions for week seven, then a decent amount of week eight shouldn't at least be new concepts, but we will go in a lot of depth in a lot of those concepts. So, yeah, week eight is a very busy week. It's 15 notebooks, which is a lot of notebooks to walk through. So just go slow. Take your time with week eight. You'll probably spend longer in week eight than you have in week six and week seven. And again, that's a little bit by design here, but it should set you up for pretty great success going into the capstone and then even beyond. So yeah, if you get a chance, please watch my week seven recap before getting too deep into the content for week eight. Again, kind of big ideas for machine learning. Week seven, week eight are machine learning weeks and predictive analytics weeks. We talked about regression versus classification, predicting a numeric continuous variable versus predicting the probability of belonging to a class. We talked about linear models, how they've been around for a couple hundred years, and they're defined by equations and are super explainable. Linear regression, or your ordinary least squares, that is going to be a regression model. And logistic regression is a classification linear model, despite its name. We also talked about basic ways to evaluate model performance. With a regression model, we use things like your R squared, MSE, MAE. For classification, we talked about your type 1, type 2 errors, accuracy, precision, recall, and log loss. We also introduced pipelines and pre-processing last week. Again, this was mostly in the live session, so hopefully you watched that. And again, this will set you up for a deeper dive into week eight. Imputation, scaling, and coding, and trying to avoid data leakage. And then we also introduced trees, which we're going to dive into here in week eight as well. And then, yeah, with week eight, we're doing a whole lot of stuff this week. So not only are we doing a deep dive into tree-based algorithms, but we're going to introduce a couple other algorithms used for regression and classification, including k-nearest neighbors and support vector machines. Then you're going to pivot over into unsupervised machine learning territory, where we review clustering and dimensionality reduction. And then finally, we enhance the material we learned last week with more metrics for classification models, feature importances for tree-based models, model diagnostics, and of course, ML, production ML. How do we bundle everything up into pipelines? How do we do cross-validation and grid search for hyperparameter tuning? And then a little bit deeper dive into regularization, which again, I also introduced in the live session last week with lasso and ridge regression models. I do not have time to go over every single one of these in an hour and a half or so here today. So again, please, please, please take the time to go slowly through the material. Finally, unsupervised learning, the clustering and dimensionality reduction. Just due to the short time of this boot camp, it's only 10 weeks. We are actually doing a high level overview of unsupervised learning in the notebooks here. So if you want a deeper dive into unsupervised learning, I've provided some resources, again, like through Kaggle and everything. The Kaggle feature engineering course will do a deep dive into unsupervised learning with k-means, the dimensionality reduction with PCA, and a couple other kind of ideas that are pretty interesting here. Last thought before I dive into the week eight content. I've done this a whole for the last like 5 years or so. 6 years, almost 5.5. So I've done kind of taught this material a whole bunch, and I've put together some study guides that past students in similar courses have found beneficial with this content. So I've attached them here. You can go download them, read them on your own time. I would start with the supervised ML study guide. Kind of goes into the big ideas of linear models, why we like linear models, what we don't like about linear models, and then other ideas around PCA, regularization, and other type of examples. Tree-based models and evaluation metrics, all that good stuff. So it's a pretty intense study guide. And then same thing for classification, mostly around, again, we'll talk about some of these algorithms today as well, but mostly about how do we interpret a classification model using things like your type 1, type 2 errors, confusion matrices, etc. So it's a good little kind of fairly quick recap of some of the things you should know around classification. And then finally, production ML. How do we kind of tie everything together into reproducible pipelines that we can then deploy? I even have a call out to Smote here, especially after Karen's post in the week 7 live thread. But yeah, how do we kind of make sure that our model through the full MLOps life cycle is sustainable and actually driving business decisions at scale? Yeah, I don't think we'll have time in the course to talk about pickling or containerization, but at least hopefully you've seen some of these things. And then, yeah, we'll do some of this today too, cross-validation, K-fold. And no worries if you haven't gone through the week 8 content. We'll explain a lot of these things as we go as well. But lots and lots of resources for you. 2 weeks for machine learning is never enough. So please take some of these additional material, additional content, the Kaggle, learn extra credits, and do some additional kind of studying on your own time here. Week 9 and week 10 are a lot lighter in content. Again, there's still some new material we'll be introducing in weeks 9 and 10, but we'll also be kind of you'll be working your way through activities that are all going to combine into one capstone project. So the capstone is going to be a series of interrelated notebooks that you're then going to execute, do, and then synthesize into some slide decks at the end. So be working on that and as well as some of the new stuff. So with that being said, if you do have extra time in weeks 9 and 10 or after the class, definitely try and reinforce some of your machine learning knowledge and content here. I know it's like drinking out of a fire hose right now, just with all the new terms, the new syntax, the new ideas. But the more that you're exposed to these ideas and content, the more they'll sink in, right? So don't feel like you have to memorize all these vocabularies. Just understand the 10,000 foot ideas of what it means to do a regression model or a classification model. How do we bring a model from experimentation to productionalization? And what I've found and what I've seen in my time in industry as well is that all of these problems are repetitive, right? There's a framework for doing machine learning, regardless of your problem. Again, I was doing problems in sports analytics, and now I'm doing problems in finance and the auto industry and building models for those other kind of programs. And it's the same idea, right? Start with your training set, figure out the algorithms you want to try, figure out how you're going to evaluate those models, do your experiments, do your runs, pick a model, deploy the model, and then monitor that model in production. I think I brought up the MLOps guide last time, but it really is a framework and a pattern, right? And the more you do it, the more you start to see the repetitive nature of it all, and the easier it is to kind of go faster and faster as you move into a more exotic type of problems. And as you'll see, this is also the baseline for kind of neural network problems for computer vision models. It's the same idea. Is this a dog or a muffin? Let me show that one because it's one of my favorite pictures. Is it having a computer vision model predicting a dog or a muffin? This is a classification problem, right? We're predicting the probability of belonging to class dog or class muffin. And as you'll see, we can actually break images down into numeric features using pixel values. And from there, you can shove those tensors into a neural network to be able to train a computer vision model. But you're still going to be evaluating it the same way, right? The evaluation metrics are still going to be your classification report, type 1, type 2 errors, your log loss. You can still going to be, the algorithm may change, but the actual process doesn't. And then when you deploy it, same idea. You're going to save it off as a file and then containerize it and deploy it to an API endpoint for model serving, just like anything else. So, again, don't get too hung up in the minutia. Try to stay and keep that 10,000-foot view of what it means to do a machine learning type problem. And then as you start getting more practice, again, it'll start going faster and faster, and a lot of this stuff will become kind of second nature. All right, so for the notebooks today, oh yeah, here's the SMOTE. Karen did some awesome work here, adding in some examples around SMOTE and imbalanced classes and imbalanced machine learning. This is in the Module 7 live session thread, so if you want to grab their Colab notebooks, you should be able to kind of open them up and see some examples. Again, really great resources for just providing more exposure to some of these different machine learning concepts that you may see in the real world. All right. Shameless plug for their notebooks. All right, for the week 8 content, again, there's 15 notebooks here. They're all backed up on my GitHub. I've run through all of them last week. So if you need help with any of the notebooks as you start doing them, feel free to reference my versions over here. But I obviously don't have time to go over every single one of these. And I need maybe about 30 to 40 minutes to do the final project. So we're gonna just hit a couple of the highlights. Um, let's see. I was gonna do decision tree. I don't know if I even have time to do k-means. We'll see. Definitely don't have time to do PCA or Tisney. All right, I think we're gonna do decision trees, k-means, and then we'll check the time. All right, so let's dive into the first notebook that I want to review with you all, which is going to be in week 8.1. We're just going to start at the very beginning here. I promised you a deep dive into decision trees, so let's do that as our first notebook here. Let's hope it's this one. Multi-class regression. Oh, it's not this one. We'll find it though. Do. Decision trees. There we go. All right. So why should we care about decision trees? Decision trees are the backbone of the most popular algorithm in machine learning right now, or in the last decade, honestly. So we've talked about linear models a whole lot, right? Linear models, they've been around for a couple hundred years. They're rooted in mathematics. People were doing them with pencils and pens and quills and ink. So they're really not difficult for computers to do. And since they're rooted in mathematics and mathematical proofs like ordinary least squares and maximum likelihood, they're very trustworthy and they're very explainable. I can always pull up the equation behind my linear model, y equals mx plus b, and to prove how I make a prediction, you just plug in the numbers in your calculator, hit enter, and voila, you have your prediction, right? This is going to hold true for both linear and logistic regression. Super explainable, rooted in mathematics and mathematical principles, and fairly easy computational wise. However, linear models have a fair amount of problems. And if you read over my study guide, I highlight them all kind of in the first page of the first study guide. What is the problem with linear models? Linear models, first, because they're rooted in mathematics and defined via mathematical proofs, they're also bound by mathematical assumptions. And these are very overlooked in machine learning as well as in kind of just predictive modeling as a sense. But most mathematical principles will come with some sort of caveat and assumption that has to be made. So, for example, within linear regression, the core premise is that there has to be a linear relationship. Second, we have a bunch of other assumptions here, including normality, right? We want our data to be normally distributed. And next, we can't have any multicollinearity. All of my variables need to be independent. This is actually where principal component analysis came out, by the way, just as a side note. PCA is a mathematical way to project your feature space into independent vectors, which is kind of cool. So typically, PCA has to be done before you do a linear model, if you're a mathematical purist. Again, a lot of us, we don't bother with any of this, but the mathematical purists out there will definitely say you have to follow these assumptions. So linear relationship, you must have normality or it's preferred to have normality in your feature set. No multi-correlation in your feature set. And you don't want to have homoskedasticity, which is basically that you don't want to see a pattern in your residuals. Your angles should be fairly reproducible and expected. So this is a con because again, most of the time as data scientists, we are not like hardcore math people. So we're not diving into the data and really kind of proving these assumptions. And no one's going to stop you from making a linear regression, even if your data has multicollinearity. And no one's going to stop you from making a linear regression if your variables aren't normally distributed. But most of the time, you're not going to have the best performing model that you possibly could, right? And more specifically, one of the bigger problems with linear models is a linearity. Linearity means that we expect some sort of linear relationship. And as we saw in week 5, you can get around this by doing polynomial regression, which adds in some non-linear capabilities. But that just increases the complexity and doesn't really improve the predictability that much. So with all these problems, we're unable to capture really nuanced relationships, especially at scale. As we start introducing more and more data with more and more kind of complexities in it, it's harder for linear models to really isolate and tease out the signal within the noise there, if you will. Um, so with decision trees, that kind of leads us into our second family of algorithms. If linear models are our first family, tree-based algorithms are our second family, and neural networks will be our third family that we'll get into later. But with tree-based models, the big idea is to try and use more computer sciencey techniques to understand and discover patterns in our data sets. So essentially, a decision tree is an if-else statement, which is kind of fun. And it's just like anything else, like a choose your own adventure book, right? We're going to, if the example that I had here was, let's say we want to predict what pet you're going to adopt. And we have, it's a multi-class classification problem. You can adopt a dog, a cat, or a rock. We can start looking at patterns in our data set, and we can find that, okay, of the people that adopted rocks, most of them traveled for work and never bothered to dress up their pets, right? And then we can start finding other relationships. Like for people that did travel, that did not travel for work, most of them adopted dogs because they like to dress up their pet, right? So now we have if-else statement. If I travel for work and if I like to dress up my pet, then I should probably adopt a dog. And we can see that in the training set that a majority of that subgroup adopted dogs. Same thing, if I travel for work and I don't want to dress up my pet, then I should probably adopt a cat, right? And again, we can determine that from my subgroups. And then finally, if I do travel a lot for work, then I should just get a rock regardless because I won't be home enough to feed it and take care of it or something. As you can see, as we start breaking down and moving through the tree, we'll start ending up with smaller and smaller groups. So typically, decision trees require a large sample size to make sure that when we do get to the bottom of the tree where we're making our prediction, we have a decent size of people or observations to provide that signal to our prediction. So let's actually see what this looks like and what a decision tree can do. And we'll talk about why then these if-else statements actually outperform linear models in certain situations. So I'm just going to install these libraries here into my lab environment. and then we'll kind of run this through. A little bit of history on decision trees. Well, linear models have been around for a couple hundred years. Decision trees do require computers to be able to tease out those if-else statements and do those breakdowns. So they've only been around kind of since the advent of kind of computers and computer theory, so maybe about 50 to 75 years. You'll see this is actually going to be the same with neural networks. Neural networks have also typically required computational power and have only been around in history for the last 50 to 75 years or so. All right, so here's our data set. We want to predict using age, sex, blood pressure, and cholesterol, and we want to predict which drug a patient responded to. So this is a multi-class classification set, just like my pet example, but instead of dog, cat, rock, we have A, B, C, X, and Y. So we want to predict these five classes here. Looking at my data, it looks like we have a lot of strings, a lot of categories that we'll need to encode. That's what these objects are. And then my drug, since we're predicting a string, it's best practice to use that as a label encoder. Oh, yeah, they're using label encoders for all of it. That's fine. This will all work out fine. Basically, we want to just make sure that we have our, yeah, there we go. Want to make our numeric data sets. I probably wouldn't have label encoded BP just because you typically want to do one hot encoding for multi-class rows. So what I mean by that is if I take a, I shouldn't get too distracted. We have a lot to do. But if I look at this BP, you'll notice that it's going to have three different categories, low, medium, and high blood pressure. But by translating that into numbers 0, 1, and 2, this can inconsequentially, or I guess what's the word I'm looking for? It can lead into our model the patterns that probably shouldn't exist, right? So if I have multiple numbers like this, it can be assumed that maybe this high blood pressure, because it's a 2, is twice as impactful or twice as influential in the model as medium blood pressure. So I think the word I was looking for was
But
unintended consequences. Yeah.
on the other hand, because they are ordered, and then they're ordinals, and so actually an ordinal like that might be fine for the model.
Yeah.
I would
I,
not, I would hot encode to the sex.
yeah.
'Cause otherwise, you're starting to look like male is better than female.
Yeah.
We don't want to do
Same.
that. But then
And
again,
we're get
we forget a little trick. Let me remind a little trick. So you hot encode two things, and so you get two columns. Then you drop one of the columns and you're fine because you still get all zeros and ones. So in a way, it's 6 of one, half dozen the other.
yeah.
So
Good on
you
the
can do
points
that.
here
You can
again.
do that, and because if you drop one of them, then if it's zero, that means it's the other one.
Yep. And so again, we'll talk about pre-processing when we get into our final activity here tonight. But as we've talked about in week seven's live session as well, the pre-processing and the data engineering of the data to make it ready for machine learning modeling is typically where your impact as a data scientist is most readily done because you are the ones kind of making these assumptions and making the decisions on how you want to impute, scale, and encode your variables to make them consumable by the model. And we have different kind of recommendations on how to do that. But at the end of the day, it's up to you. And for example, if you want to use a standard scaler versus a min-max scaler, that's a decision that you have to make or iterate on and see if it actually does make a difference. But to keep moving on here, we've encoded our drug to 0, 1, 2, 3, and 4. And now we should be able to build our classifier. Just like with regular predictive modeling, we want to see if we have any correlations. One quick note, correlations by definition are linear correlations. So as we've talked about, these are really good for linear modeling because we need to have a linear correlation or relationship ready to go. For decision trees and tree-based models, the assumptions here do not matter. So we don't even have to have linearity. We don't have to have any of this. We can even have multicollinearity, and the decision tree doesn't care. So the correlations, if we're building a tree-based algorithm, still are good to know, just so you know that there are impactful features here. But as you may see, once you build a tree-based model, the most important feature may not actually be the most correlative feature. So that's just something to look out for. And there's always nuance with a lot of these modeling topics. But looking at this, it looks like blood pressure and the sodium to potassium ratio have some strong correlations with our target here. And now we're ready to also looking at our targets. It looks like we have some imbalanced classification here as well. Drugs A, B, and C have less participants than drugs X and Y. So maybe if we had more time, we could do an imbalanced SMOT adjustment over under sample adjustment. But we'll leave that as an exercise for the reader. All right, now to the fun stuff. Let's actually build a model. Notice for my model here, we are building a decision tree classifier. If I was doing a regression problem, this would be a decision tree regressor. And we gave it a max depth of 4, which means given my if-else statements, I only want it to go 4 levels deep. And if you don't have a lot of data, you probably want to restrict your tree from going too far out. As we mentioned, when you get to the final layer of the tree, there's only, if you don't have enough data, then you're going to have small samples that dictate the prediction. And that's not really what you want. So we're going to do a max depth of 4 here. And wow, we have trained a decision tree. That was quick. And we can see our predictions, and we can look at our accuracy score. So we have an accuracy score of 98% on the test set, which is pretty cool. And if we even wanted to, we could do a classification report. Oh my God, of my Y test set and oh my God, I can't ever do this autocomplete. Tree predictions. Let's see if that worked. Cool. So you can see here, oh my God, that yeah, we are able to predict everything like really well, which is pretty nice. And notice that again, we have pretty small samples for some of these, but it is what it is. And then this is really what I wanted to show. We're grabbing this plot tree function from scikit-learn up here at the top. Yeah, from scikit-learn import plot tree. And this allows us to see this if-else decision tree at in reality. So if you actually look at this, we can see, where's my pen? Boom. We have a max depth of 4, right? 1, 2, 3, 4. And these are prediction layers, right? When we get all the way to the end here. I think we're predicting class 1, class 2, class 3, class 4, class 5, or something like that. But you can see here that we're able to predict based off of conditions. And it's not exactly telling us what these conditions are, but you can see that if column 3 is less than or equal to 0.5, then you're going to go down here. And if column 0, column 1 is less than or equal to 50, then you're this prediction, else you're this prediction. All right, same thing over here. If x.4 is greater than 14.627, then we're going to be this prediction up here. So that's kind of the way that we start parsing our way through the tree. And if you're curious about how the tree found these cutoff values, 14.627 seems pretty precise. That's the experimentation and the training. Behind the scenes, when we fit the model, it's going to iterate a whole bunch of times until it converges on kind of the best values for these trees. So what that means, training some of these decision trees can take longer than a linear model, especially if you have a large amount of data that it needs to fit across. And as we'll see, most of our tree-based models will actually incorporate an ensemble of trees, of more than one tree. And so if I'm training a model that's fitting 1,000 trees on 1,000,000 rows of data, it's going to take time and computational power to do that. So that's going to be one of the other trade-offs, right? As we start talking about tree-based models and neural networks versus linear models. Linear models are very computationally light. Computers can calculate the optimal equation from a mathematical proof in like milliseconds. But for these tree-based models where we're going to be doing iterations and experiments and trying to converge on an optimal solution, it takes time for the computer to iterate and simulate that. Same thing with neural networks. As you'll see when you're training a neural network, you're going to have what's called forward and backward propagation, which is basically where the computer is tuning the neural network to give it the best performance possible. And that takes time, every single one of those iterations. And tree-based models are no different. They take time to converge to the optimal, I guess, if-else statements that'll actually maximize the model. Let me actually look
One,
at the,
one thing I
yeah,
really
go.
like about people, especially the beginners, looking at decision trees like you have of the graph. If you think about it, old-fashioned programming, I might sit and write a bunch of if-then statements to implement a bunch of rules. But now instead of my sitting and writing those rules myself, I actually have an algorithm that can write it for me. And there with a tree, a decision tree, it's pretty obvious exactly how that works. I just
Actually,
find
I'm
it
gonna
really
do,
cool. I just find it really
I'm,
cool that way.
yeah, I'm gonna do this again just because I want to see if this will work. So one other thing to note, like we mentioned, decision trees, they are converging on these optimal numbers, but it's not guaranteed that it'll always find those same numbers. As you'll see, kind of with decision trees and random forests, they take some kind of randomness in them as a starting seed for when they start to iterate and converge on these numbers. So typically for random forests or decision trees, we want to include a random state to make our decision tree reproducible. Hopefully, it's random states. Yeah, random state. I don't know what it's mad at me about. And so let me actually train. I'm going to train a second tree. Notice that this first tree, we did not provide it a random state. So the second tree, I want to try and, oh my God, I want to give it a random state, and then I want to see if the tree cutoff is different. So let's make our second decision tree. And if I run this, oh no, it gave me the same values. I was hoping it'd be different. Womp womp. I guess maybe I'll have to do this with a random forest. But yeah, I guess it's giving me the same numbers here. But when we start doing more complicated trees, you'll see I was probably able to converge. There's only like 200 rows. As you start having kind of larger and larger data sets, you'll see that you need to make it reproducible by controlling the random seed that your tree starts from to start training. Anywho, I think that's good enough for decision trees. Um, the next step on this, hopefully that's saved. Perfect. The next step from a decision tree is expanding this into, let me make sure we have, oh yeah, the taxi trip. Is to expand this into what's called an ensemble. So let me actually pull that up as well, which will be the random forest. Regression trees. Let me make sure. This is at least doing a random forest. It's not. It's doing a decision tree. All right, so we're gonna skip to I think it's gonna be 8.4, 8.3, 8.3. So let's jump to 8.3 here. So I'm gonna jump into 8.3's media set, and we're gonna plop on down to random forest. I'll come back to SVMs here in a second. I'm not going to show the notebooks for them, but I will discuss them as an idea here in a second. All right, so now that we have one decision tree, as we mentioned, a decision tree by itself is pretty good. There's a lot of pros to decision trees. Some of the pros with decision trees include the fact that we do not have any linear assumptions that we have to deal with, and that they're able to really track non-linear effects. Because there's no mathematical equation or anything that we're trying to converge on, the if-else statements just do what they need to do. It doesn't matter if it's a linear, if it's a polynomial or an x squared. Like there is no equation, so it can just do what it wants. So this is why tree models are so popular today because nobody wants to have to deal with multicollinearity. Nobody wants to have to deal with linearity and linear modeling and linear assumptions. Just throw a tree at it and it'll probably be a pretty good model, right? As I've said, the only big trade-off that I see with tree-based models is tree-based models require computational power and they're a little bit harder to explain, right? With an equation, it's really easy to explain how you got the prediction. With a tree-based model, it's a lot more difficult. And again, if you're creeping on some of the Kaggle learns, you'll see they have a whole course on model explainability, which I think is really, really interesting because this is a big problem. How do you explain how your model works to non-technical stakeholders? And when you start getting into tree-based territory, that's where this problem first starts to emerge. Working in baseball, I was literally for a time, my first couple of years, I was not allowed to train like an actionable model off of a tree-based algorithm just because it was inexplainable to coaches and players. So even though I knew it was a worse model based on the metrics, I would still just have to use a linear regression as opposed to a XGBoost model, which is kind of interesting. But now more people have been educated enough that we're able to, and there's better ways to now explain these types of models to try and kind of get that buy-in. My last note on this is why you'll hear neural networks considered a black box algorithm because they are even more difficult than the tree-based family to explain what they're doing, right? Like at least I can say that with a tree, it's doing if-else statements, and I can pull out feature importances, which is basically just a visualization of how many times a feature was used to make a split. But with neural networks, it becomes a lot more difficult to explain what each of these neurons are actually doing. Anywho, let's dive into this example. So the problem with a decision tree, just by itself, is that a decision tree is very prone to overfitting. Overfitting means that it finds patterns in the training data that doesn't exist in the real world in kind of unseen data. It overfits signal that's not actually there, right? So one way to mitigate that risk of overfitting with a decision tree is what's called an ensemble or a forest, right? Let's train 100 trees. Each of these trees will be trained on a different sample of the training data. So they're all going to be slightly different in terms of their splits and their criterion. And then to make our final prediction, let's just look at how many of these 100 trees told me to predict dog or cat or rock or drug A, B, or C. So we're taking the collective prediction of the forest versus an individual prediction of the tree. And it's been proven that by having multiple trees kind of do that prediction or being in charge of that prediction, it removes that threat of overfitting, although tree-based models can still overfit pretty poorly. And it encourages more kind of variance and more reliability on unseen data, which is kind of a huge plus here. So a random forest is exactly kind of what it sounds like. It just uses multiple trees as is. But beyond random forests, we get into what's called boosted forests. So you'll see there's a lot of different types of boosted forests. I think I brought up cat boost before, light gradient boosting, extreme gradient boosting, XGBoost. All you need to know with boosted forests is that what do you think the problem is with a regular forest? It treats every single tree as equal in the forest. But as I just mentioned, every tree is trained on a different subset of data and converges to different cutoffs. With that being said, each of the tree in the forest is not performing equally. Some of the trees in my forest are going to be really, really good. and some of the trees in my forest are going to be really, really bad. So why am I taking just a straight average of all of my trees? Why am I treating all my trees equally when I know that they are better trees than others in this forest in terms of this predictive power? So all that a boosted tree does at a very high level, it boosts the good trees and penalizes the bad trees in the forest, right? So it's a weighted average in all that it's in all but name. So we're going to weight the good trees higher and lower the weight of the bad trees in terms of making our final prediction. And if that sounds intuitive and common sense, it is. It's just a lot more harder to program. So it took a few years to kind of program this out. But these boosted trees and boosted forests are almost the gold standard. I think like they're the most popular type of predictive algorithm today, even beyond neural networks and generative AI models, all that good stuff. Classic machine learning, classic predictive analytics is like peaked with boosted trees and boosted forests. So specifically, you'll see three variants of the same boosted algorithm floating around. Gradient boost, right? Just gradient boosted trees. That's in scikit-learn. Extreme gradient boosting, which is also known as XGBoost. That is a little bit, it takes a little bit longer to train. It's a little bit more computationally heavy, but it typically is the best tree-based algorithm. And then my favorite, which I have to give a special shout out, promise I'm not sponsored by Microsoft, light gradient boosting, which was originally developed by Microsoft a few years ago. And it's basically XGBoost, but it's a lot faster just because it doesn't do as much crazy stuff as XGBoost does. So sometimes XGBoost will outperform it, but I am an impatient person and I want my models to train quicker. So I like using a light GPM. Um, yeah, I've also mentioned Cat Boost. Cat Boost is basically if you have a data set that has a lot of categories in it or a lot of like strings and objects, and you don't want to be bothered with all the different encoding drama that Karen and I were talking about with label encoding, one hot encoding. Cat Boost takes care of all of that for you. It's great. It tries different encoding techniques and it fits them all across your different trees and it boosts the good trees and it's great. So if you have a data set that has a lot of categories in it, Cat Boost may also be good for you as well. But again, Cat Boost, Light GBM, and XG Boost, those are all independent libraries to scikit-learn, so they can be a little bit annoying to install. And if you actually look at the history, XG Boost was actually like it stabilized in like 2018. So these are all fairly kind of recent. Yeah, 2019, 2018. So it's been around for a little under a decade now, but pre-COVID, the data science world was going all like hyped and viral of these boosted trees, especially when it has extreme in the title. Like who doesn't love a good big red X? Anyway, now nobody cares about gradient boosted trees and it's all about large language models and stuff. But again, you'll still see these tree-based algorithms in a majority of business use cases. So what I wanted to demonstrate here is we're going to be predicting how much a house costs, which is a very classic example here. And we're going to be using a random forest and an XGBoost model. So again, we're going to be comparing between a single decision tree, a regular forest, and then a boosted forest. And we'll see how they do differently. So I'm just going to go ahead and slam in a few of these solutions, load in our data. We have 20,000 rows, finally a decent data set. That's the other big thing with tree-based models. You need to have a lot of data. A tree-based model that's trained on a couple hundred rows will actually like not perform very well and will almost certainly overfit even if you do a forest, right? The linear models shine on smaller data sets, but as you get into larger and larger data sets with more nuanced patterns, you really want more of these advanced algorithms. But I've had people like just throw a random forest at like a data set of 200 rows, and I'm like, what are you doing? And I show them that the linear model like literally matches performance. So just make sure there's a couple nuances there. So make sure to keep track of the size of your data. Here we're going to load up a random forest and an XG boost. Notice that we are defining a random state to make sure they're reproducible, and we're initializing each one with 100 trees. So there should be no difference to the number of trees in both of these forests. The only difference should be that one is a boosted forest while one is a regular forest. So all we're doing here is that we're training both models, and we're going to look at how long it took to train them here in a second. And hopefully, take your guesses now. Put your guesses in the chat as to which model you think is going to take longer to train. But we're going to see it here in a second. So now here, what we're doing is we're measuring the inference time. How fast does the model make a prediction, right? Especially if we're running this model live during the real world, we need to make sure that we're able to make predictions quickly. All right, and now we're grabbing some performance metrics, mean squared error and R squared. And now let's see the performance and the timings of each model. So we can actually see here that my XGBoost model is more accurate than my random forest. It has a lower mean squared error and a higher R squared. So success. Yay, high fives all around. The more complicated algorithm was better. Hooray. And now we can look at the training time. And looking at our training time here, we can see that oh yeah, the random forest took forever to train, but the XGBoost was actually really quick. I would have thought the XGBoost had been a little bit slower than that, but maybe there's some caching and stuff going on with the data sets. But yeah, as you'll see, random forests are very inefficient, both in terms of how they're training and also how they make predictions. We can grab some standard deviations here. And let's look at everything all at once. So yeah, we can see, I think we're supposed to have printed that out, but whatever. Let's look at the predictions here. And again, this should hopefully validate the fact that the XGBoost model outperformed random forest. Uh, Cool. So in summary, where I wanted to get to with decision trees, and now I think we have to pivot to the last activity. But big ideas here. Linear models are great, and they're really great if you have constraints around computation or data size, right? If you have a small data set and you don't really like have like big computing power, then a linear model will be just fine, right? And especially if you go that extra mile to make sure that you meet the linear model assumptions, you're using independent features to reduce multicollinearity. You proved there are correlations in a linear relationship. Then yeah, your linear model will be fine. But as you start moving into big data, right, and you have to use cloud computers and you have larger data sets, we have to start looking at other types of algorithms, including tree-based algorithms. Tree-based algorithms been around for 50 to 75 years. They're rooted in computational programming principles, specifically if-else statements. And as we've seen, they do not need any assumptions, and they can even find nonlinear effects as well, which are great. Tree-based algorithms peaked in about 2018, 2019 with XGBoost and LightGBM and CatBoost, and those are still the gold standard to this day, as you'll see tree-based models running in production at every organization that you'll encounter in your data science career. Cool. All right, that's checkpoint one. With that being said, I'm now. Any questions in the chat or anything on tree-based models? No? Awesome. Well, I think that's a good
Let
checkpoint.
me look. Let me look again.
No, you're good.
No,
And so
no.
the next couple sections in the class go into unsupervised learning and dimensionality reduction. I don't have enough time in my live session to deep dive into clustering and dimensionality reduction. I would spend another hour just talking about both of those things. But definitely recommend you explore those on your own time in the media sets and also with the extra material I provided. They're not going to be critical to the capstone or Part of the targeted depth of the class, like I've said, the targeted depth for this week and the last 2 weeks is on supervised machine learning and then moving that supervised machine learning into production. So that's kind of where we'll skip ahead to. 8.6 goes into evaluating models. We'll incorporate some of this into our last activity here in 8.8. But one thing to point out is that tree-based models can be evaluated exactly the same way. We can look at your R squared. We can look at your predicted versus actual plots. We can look at your mean squared error. But when we get into explaining how a tree-based model works, we have to pivot to something called feature importances. For those of you paying attention last week, you may have noticed in the linear and logistic models, we actually used coefficients to help proxy how important a feature is. That's actually doable in linear models if you've scaled and standardized your feature sets. But in tree-based models, it becomes a lot more clear. Feature importance is defined as how many times that feature was used in all of your trees to define a split to make a prediction. And it's a great way to explain why a tree-based model is making the prediction it is. So in this example, we're predicting California housing prices again. And we can see that the most important feature was your income, which again makes sense, right? If I want to predict how much I'm going to buy this house for, I should probably know like how much you make, right? That's going to be one of the main drivers of the price of the house that you're going to be able to afford. We also have location, latitude and longitude, and the age of the house, which is really interesting as well, right? Where is the house located and how old is it? Maybe in this feature set they didn't have the square footage, but I also see square footage. Oh yeah, they didn't have square footage, but square footage is obviously also going to be a big driver of like how much this house is going to sell for. And typically like feature importances as a gut check, right? Is the model finding patterns that I, as a human, would expect it to find? And in this case, the answer is yep, this feature importances flies through the gut check really easily. And sure, there may be some times that a model will find features that it thinks are important that I wouldn't have thought of. And at that point, you have to make the decision as the data scientist. Maybe if that model is more accurate, maybe you trust it. But I don't trust any machine learning algorithm. All models are bad, but some are useful. It's a quote I'm gonna have. I used to have it printed out. It's great. All models are wrong, but some are useful. That's one of my favorite quotes. But yeah, all models are bad. Even ChatGPT is bad, but sometimes they can be useful. But anyway, if a model has a feature importance that I would be surprised about, I may use that as a negative when I'm evaluating the model. I'd be like, huh, you probably found some signal that's actually noise, so I don't trust you as much as I should with one of these other models that match kind of my gut check. But yeah, that's kind of feature importance here, and we'll come back to this in a second. And we have some other ones. Again, we introduced a lot of these last class in week 7 about your type 1, type 2 errors and your classification reports and things. And then we're not going to do clustering during the live session today. 8.7 and 8.8, they go into pipelines and grid search, which I'm going to do here in the final activity. We introduced pipelines in week 7 for pre-processing. So here you can see we're doing a standard scalar, then a PCA for dimensionality reduction and to remove multicollinearity, and then we run a k nearest neighbors classification model. Um, Long story short, k nearest neighbors also typically requires its data to match the same as linear models. So again, this is also a way to do a linear model to meet all the assumptions of independence as well. And we'll go over cross-fold validation here in 8.8. But basically the idea is when we define a train test split, right? We take 20% of our data and hold it out. What if we got lucky, right? What if the 80% that we trained our model on was just a really good subset of the data? So with k-fold cross-validation, which we'll get into, I guess this is grid search. With cross-validation, the idea is Let's actually try multiple different train test splits and then take the average performance of my model across all of those different train test splits, which is a nice way to ensure that we weren't just lucky with our train test split. And then finally, the grid search and hyperparameters. When we get into more complicated models like decision trees and random forests, let me actually pull up the random forest here. You'll see that they come with um, hyperparameters, these parameters here. For example, the one I always bring up as an example is the number of trees. How do we know to use 100 trees? Maybe 50 trees will be better. Maybe 200 trees will be better. You don't really know until you train a model with 200 trees and see if it's better than a model with 100 trees. So that's called a grid search. We're going to try a whole bunch of different features, different hyperparameters, and train a whole bunch of models and see which one is best. And this is where things like keeping track of your model experimentation and your model runs come into clear clarity. So we can see here in our hyperparameter tuning, we're testing to see if 3, 5, or 7 neighbors is best, and then using 2 or 3 principal components is best. So we're going to do our cross validation. N splits equals 5 means we're going to try 5 different train test splits. We're then going to do a grid search for each of those 5 splits. We're then going to run all of these different models. One, two, three, four. I guess you got 6 different models. So it's going to run 6 different models for each of those splits. So it's totaling 30 splits, 5 folds of 6 different parameter combinations. It trains 30 models and then it spits out which one was best here at the end. And you'll see that 3 neighbors with 3 components was the best model out of them all. And they actually improved your accuracy by 3%, which is great. So that's kind of the idea with hyperparameter tuning and cross validation. I like to say that algorithm selection probably accounts for like 80% of your model performance, right? Just choosing the right algorithm between linear regression and random forest and XGBoost and neural network and cat boost. Choosing the best model gets you 80, 85% of the way there. And then tuning your hyperparameters and ensuring your cross validation and stuff, that'll get you another 5 to 10% of the way there. And then the last 10%, I guess, is this randomness and how good your model actually is. All right, I'm gonna try and end here at 2:30 or 3:30. So let's kind of blast through the final exercise here. All right, so the last notebook that we're going to go over is 8.8, which is going to be building a, it's kind of your keynote for this week. We want to, using everything we now know about tree-based algorithms and evaluating trees and evaluating classification models, I want to build a predictive model that predicts whether or not it's going to rain tomorrow in Australia, which is kind of a fun problem. So let's get after it. We're going to load in all of our data and we're going to just give this a go. I'm also going to probably load in XGBoost as well here. So let me also do a pip install XGBoost, which should already be in my library. And then we can do a XGBoost import XGBoost classifier. How fun. Great. So we're going to load in all of our different libraries. Notice that we're bringing in all of our pre-processing, scaling, encoding. We probably should have an imputer, but it's fine. We're loading in our algorithms, logistic regression for our linear model baseline, random forest classifier, and our XGBoost classifier. We're loading in our metrics, including our classification report and confusion matrix. And I think that's it. So let's do our end-to-end kind of experimentation here. We're going to load in our weather data and take a look at it. There's a couple things that I want to look at. So looking at my data, it looks like we have a whole bunch of data. This is typically the first thing I look at. We have 145,000 rows. So that is way more than enough to train a machine learner, to train a tree-based model. So that's great. A few other things I'm looking at. Most of my data set is numeric, which is great. Again, you need the more numbers, the better. It's easier to deal with your stuff by having numeric data. And then the last thing I'm looking at is the number of null values. So it actually looks like we have a lot of null values in our data set. As I'm looking over this, we only have 75,000 that indicate if there's sunshine or not. 86,000 that tells me if it's cloudy at 3 p.m., etc. So that's not good. Usually we would want to impute those. For the sake of time, though, we're just going to drop all missing values. YOLO. And we're down to 56,000 rows. So this is actually kind of bad. If I was doing this in the real world, I would be concerned. We ended up dropping 90,000 rows, which is a lot of data to just delete. But in the case of this example, and to keep it simple, we're going to drop all those rows, and 56,000 is still more than enough to train a good tree-based model. All right, so we're not going to do any imputation, and we'll leave that as an exercise for the reader if you want to do that on your own. We reviewed how to do that in the week 7 lecture, by the way. Some things to note is we want to make sure that we don't have any data leakage in predicting tomorrow's weather. So you can read some of these hints here. Some of the things we're going to do, we're going to just clean up some of our columns. We're going to rename rain today as rain yesterday, and then rain tomorrow as rain today. And then from here, we're going to just minimize our data to only be located within Melbourne. Again, we don't want to predict if it's going to rain in all of Australia. There's a lot of high variability in that versus like the desert versus the coast. So we're just isolating our data to only within Melbourne, and we're down to 7,500 records. So again, this is where I would be like, I wonder how many of those null values that we dropped were actually around Melbourne, in which case I'd probably bring them in here. 7,000 is still more than enough for a tree, though. But note that I probably would have used more than this, depending on the null value problem above. All right, we're going to do some feature engineering. All we're going to do is extract the season from our date. This is going to create a new categorical column for us to encode: summer, autumn, winter, and spring. And then we're going to map those dates to seasons and drop the date column. And luckily, I've already done this. So feel free to reference mine in GitHub, or whenever I upload this live session notebook as well. But for the sake of time, I'm just going to start copying code over. So let's go ahead and run it. Boom. If all goes well, we should only be in Melbourne, and we should have a new column for season, and we should have dropped the date column. And if we really want to see what this looks like, let's do a dot season dot value counts. And we should see that we have about 1,900 observations for all seasons, which is pretty good. All right, so let's go ahead and build our model. We're going to try a couple different algorithms here. So let's define our feature set and our target. Our feature set is going to be every single column, and our target's only if it rains today or if it rains tomorrow. And we can have a look to see if we have an imbalanced data set. Probably gonna type this one out. And we can see that yes, we do have an imbalanced data set. Let's actually do the math here. 1791 divided by 1791 plus 5766. And only 25% of the time, 24% of the time did it actually rain. So if I wanted to build a model, I could just say, no, it never rains in Australia and Melbourne. And my model, if I just say, no, it doesn't rain, is going to be right 74% of the time or 75% of the time, which is kind of fun. But obviously that's a bad model, right? So I just say that as an example to make it clear why imbalance is such a problem. We talked about this last week with churn. Karen's got their note about smote and everything. Definitely recommend reading that up on your own. Note that we're not going to do anything about it, but it's good to observe it. And again, as an exercise for the reader, I encourage you to try an oversampling method to see if it improves your model. All right, so let's split our data into a train test split. We're stratifying on why we do this for classification classes to make sure that we keep this proportion of 24% in both my train and my test set. Now we're going to define our pre-processing pipeline. For our numeric features, we're going to want to scale them. And again, we're using a standard scaler here. For our categories, we want to encode them. So we need to define which are going to be my numeric and categorical columns here. And again, let's print these out just so we know what they are. Print numeric features, and we'll also print out the, sorry, I can't type in this IDE. Categorical features. Great. So here we go. So my numeric features are temperature, rainfall, evaporation, the amount of sunshine, wind, humidity, pressure, clouds, and temperature. And my categories will be the location in Melbourne, the direction of the wind direction during the day, whether or not it rained the day before, and my season that we feature engineered from the date. So now let's define our pre-processing pipeline. All that we're going to say here is for my numeric features. For my numeric features, I want to run them through my numeric transformer. For my categorical features, we're going to run them through my categorical transformer. And again, if it was up to me, I would have added an imputation step here as well, like we did in week 7. But I'll leave that as an exercise for the reader. Time to throw in our random forest. So let's go grab our random forest. And this looks good to me. We have our steps. We're going to do our pre-processing, our scaling and encoding. Then we're going to train our model, and the pipeline will take care of all that organization for us. That is the beauty of the pipeline. Now we're going to do our hyperparameter tuning. For our hyperparameter tuning, these are all going to be based on the classifier on the random forest. N estimators is the number of trees. Max depth is how far, how big do you want each tree to grow to. And then min sample split, I'm not sure what that does, but it's in the documentation. But we're going to try building all of these models out. Notice that we're going to end up building 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 2. It's going to be about 24 models. Split. I don't know why we did a train test split. We definitely did not need to do this. But since we haven't specified, assuming we haven't specified a train test split, we're going to use our k-fold cross-validation. Again, we're going to basically do 5 train test splits. And the beauty of this is that every row will be both a training set and a testing set after all 5 folds have been completed. And now we're able to do our full grid search. So let's define our grid search. Oh, they are fitting it on X train, Y train. That's funny. I think they probably shouldn't have done that. But whatever. I think this probably should just be fit on X and Y, right? Am I crazy? Because of
No,
this, the cross.
actually, what you'd want to do is to make a train test split. Put the test aside for
Oh,
good.
the test is
Yeah.
like, yeah, yeah, that's the holdout.
Your
Okay,
final
I get
thing.
it.
And then you're going to use the
Yeah,
Y
yeah,
train,
yeah,
and the cross validation is going to
yeah,
happen
yeah,
within that to
yeah,
as
yeah,
you
yeah.
do your hyperparameter tuning.
Karen, thanks for, I'm just going crazy because I'm going too
Yeah,
fast. So yeah, essentially what we're
yeah,
doing
that's
here,
because we're doing
it,
cross validation. We don't have to do a separate evaluation set.
yeah, yeah,
It kind of makes them along the way, and it's actually a more efficient, a better way.
yeah,
And then we have that test, like I said, that's like our gold standard in the end to go, okay,
yeah.
let's see how really great our model is in the end.
Completely unseen data. Yeah, absolutely. So we're doing training,
Virgin data,
validation, and
virgin
test.
data,
Yeah,
like
virgin data,
like
the untouched
Madonna,
data.
like
Yeah,
Madonna.
yeah. I love it. So yeah, we're training our model with just the training set. Um, Even though that training set, we're then doing another train test split on it, essentially with this cross validation. So you may also see training, validation, and test used in vernacular whenever you're researching this on your own. And that's essentially what we're doing here. Within each fold, we have our training and our validation set. We're going to do that 5 times. So every row is part of the training and validation. And then after we've done our cross validation and hyperparameter tuning, we're then going to run that through our test set, our virgin data that's been untouched, and we can see exactly like how well our model should work in the real world. Thanks for that clarification. I was going a little crazy there. So notice that we're totaling 5 folds of 12 different models. So we're going to be training 60 models here. Probably should have kicked that off first. We're gonna let this go. It's actually going pretty quick, taking less than a second, half a second or so to fit. I probably could have done that math better. Is this 3 times 2 times 2? That's 12, yeah. So yeah, 3 times 2 times 2 times 5. So that's why we're making 60 models. Notice that this gets very crazy if you have lots of parameters you want to tune, right? So if you want to do 5, 10, 15, 20, 25, 30 trees, that's going to take you all night. And that's what people do. They kick off a model training at like 5 p.m., go home, come back at 9 a.m. the next day, and it's churned its way through thousands of different kind of model iterations. Again, that's that compute intensiveness that tree-based and even neural-based networks require to kind of get you your most optimal model.
If it's homework, you start it and go to bed and do something
Yeah.
else, and then in the morning it'll be ready.
And no, that's you couldn't cram. And back when I was doing my master's a long time ago, yeah, you couldn't like cram training some of these big models because they're like, oh shit, it's due in an hour, but it takes 2 hours for the model to train. But yeah, we can see here that we trained 60 models. We have our pipeline, and at the end of the day, the best model that it's found was none for max depth, which is funny because that actually defaults to 100. So I don't really know why they did that, but none for max. Oh, max depth is the depth of the trees. So the max depth is actually going to default to, oh, it is none. So we'll just let the tree grow as big as it can. Min samples of 2 and N estimators of 100 trees in my forest. And we got a score of 85. Let's kind of run through this real quick. Display your model's estimated score. We're now going to evaluate how good this model actually is on the test set. So remember, the test set is the unseen data. And on the test set, it's got an 84, which is very close. So that's actually pretty good. Then that implies to me that we don't suffer too much from overfitting. Let's grab our predictions and generate our type 1 and type 2 errors. And with our type 1 and type 2 errors, we see that our model's not that good on predicting if it rains or not. We only have a true positive rate of about 50%. So about half the time that it actually did rain, we only predicted it correctly half the time. So that's not great. And again, I'll put most of that down to the imbalancedness of the data set. Plot the confusion matrix. And again, we can see that of the 350, 60 times that it actually did rain, we only actually predicted it correctly half the time, just about. So I would not trust this model if I was a weatherman. Let's look at the feature importances. I'm just gonna grab those real quick. Oh yeah, the positive rate is not very good. Let's grab our feature importances. Oh no, Colonel died unexpectedly. That's not what I wanted to see. Womp womp. Sure. Oh my God. I guess we'll
Cyber
review the rest
gremlins.
of that through my notebook.
Cyber
And
gremlins.
yeah, that's why this IDE is not my favorite. But going through the feature importances, you'll see that of our model, the ones that this is why I always back up the notebooks in the earlier in the week. Looking at the feature importances, the humidity as late in the day as we can measure it. So again, 3 p.m. was the latest measurement we had. So that would be like today at 3 p.m. What's the humidity and what is the pressure? And those are the most important features on if it rains tomorrow, which to me makes sense. I think that passes the gut check, right? If it's very humid, right, with a low pressure system or something at 3 p.m., then yeah, it probably is going to rain tomorrow, right? And we also see the amount of sunshine and the amount of wind and pressure. Like, yeah, all this kind of indicates if there's not a lot of sunshine and there's a lot of wind, then yeah, this probably will impact some of the things. Some of the other ones that stood out to me was the fact that whether or not it rained yesterday is actually not that important. So that implies that the rain on consecutive days, they're independent events. Just because it rained today doesn't mean it's going to rain tomorrow. We need to look at some of these much more complicated features like humidity and pressure to be able to actually forecast if it'll rain tomorrow. So I thought that was interesting. And then last thing here, try another model. So we went through all this again. This is what I wanted to show in the kernel with XGBoost, but I'll run that after class on my own. We can try a logistic regression. Notice we have less hyperparameters to tune for in logistic regression, typically just changing the regularization strategy. And so we're going to train 20 models and notice how fast they are, zero point 0.0 seconds. Computers can solve a logistic regression in no time at all. Contrast that to the half a second to a full second it took to train a random forest. So it trained them all pretty much instantaneously. And if we look at our results, it actually is a slightly bit better. Even though the accuracy score is worse, it's a little bit better at predicting if it rains tomorrow or not. So, yay, maybe we choose logistic regression. And then last exercise would be to do this again for XGBoost and see the XGBoost model versus logistic regression and the random forest. And that's it. So then once you've found your model, we'll talk about this more going into the capstone week, but this comes back to my idea of productionalizing your machine learning model. Now that you have a model that you're happy with, how do we productionalize it? And that goes to saving. How do we save our model so we can reuse it later? And then how do we deploy and host our model so that other people can use it as part of a data engineering pipeline or a live application that someone's interfacing with? We're right on the money here. So let's just wrap things up and be out of here at the bottom of the hour. Big ideas that I want to make sure we go over in week eight. Week eight is intermediate advanced machine learning. Couple things I want you to really take away. First, our targeted depth in this boot camp is supervised machine learning. So even though in week eight you'll touch on unsupervised as well as dimensionality reduction, those are not going to be depth topics that I will discuss in lecture or in the capstone. However, big takeaways from week eight should be tree-based algorithms, right? We introduced them last week. We're going heavy in depth with them today. You should be able to talk about the pros and cons of linear models, as well as the pros and cons of tree-based models, and compare and contrast those two different families of algorithms. We talked about decision trees as a computational program of if-else statements. We talked about forests of trees, of using multiple trees to make those predictions. And finally, boosted trees, which are the gold standard now for many supervised predictive problems in the real world. Then we went into a full end-to-end pipeline of Australian weather data, gathering our data, cleaning it up, dropping null values, renaming columns, feature engineering to generate seasonality columns, and then building a predictive pipeline end to end, including cross-validation for to make sure we don't be biased by our train test split, and hyperparameter tuning and a grid search to make sure that we're using the right number of trees, etc. We then built those pipelines out, compared multiple different models, logistic regression versus a random forest versus XGBoost. We looked at the feature importances to make sure that we understood our model explainability, and then we talked about how we would save and deploy this model for production use cases down the line. Hopefully this was a fun class. I enjoy Week 8 a lot. It's a lot of material, but just go slow through it. read up on my study guides, read up on Karen's knowledge and the additional kind of extra credit assignments. And you're on the home stretch here. Week 9, week 10, a lot less new material. Instead, we're going to be focused on putting these all together into shaping kind of our final capstone project for the portfolio, which we'll kind of walk you
And
through over the next couple of weeks.
and don't hesitate to post any other questions. We will get to them.
Yeah. Please post questions in the chat. We check the chat every day. So if you have questions about any of these models, algorithms, use cases, or you find an interesting article, or you have a question about any of the notebooks, just reach out and we'll answer them to the best of our ability. All right, I gotta hop to another call, but thanks everyone for the time. George, I appreciate you hopping on and sticking on. I know it's a lot of content here. Let us know if you have questions as you go through the labs over the next